Hello, everyone. Welcome back to another DevOps Live meetup, virtual meetup. Tonight, we're going to have a great speaker going to be talking to us about some exciting stuff with Mesh and Kubernetes. But before we take off on that, whoever didn't attend in the last few meetups, just want to let you know that our DevOps Days, Dallas, has been postponed till August of next year. So just keep a look at our website. Let me go ahead and bring it up real quick here. This is going to be our DevOps Days 2021 website. It's right there. So you could just go there. But you don't have to wait until next year if you want to attend a virtual DevOps Days event. We have a lot of them happening. Just go to devopsdays.org. There's a lot of virtual DevOps Days events happening around the world. I know there's one coming up soon for Chicago, and there's one in Bogota, Colombia coming up. And so, just go out. Some of them are free, some of them are paid. So, just go check them out, see which one you want to attend, check out what speakers are talking, and, just come out and share with everybody. They're going to be live, so you can ask questions of the chats, of the talks. There's going to be a lot of fun, exciting things happening. So go check it out, devopsdays.org. So right now, what I'm going to do is I'm going to go ahead and bring in Andrew Jenkins. And hey, Andrew, how you doing today?
Hi, good. Thanks for having me, Mike.
Great, thanks for coming on. Yeah, and Andrew is if you search him up on Twitter, he's the not that Jenkins. So I don't know what the joke is behind that, but I could just imagine people thinking that you're the owner of Jenkins or something like that.
That's it exactly. I started getting emails about the Jenkins server failing builds. I'm not that Jenkins, different one.
That's hilarious. So yeah, tonight he's going to be talking to us here. Let me bring it up on his slide decks. We got here. Choose your fault domains carefully. So having to deal with mesh apps architecture and Kubernetes. So these are two very hot topics. I mean, mesh is something that's coming up a lot. So I'm going to go ahead and drop off. I'm going to let Andrew take it from here.
All right, thanks, Mike. Mike's offered to collect some questions.
That's right.
And interrupt, and I love that kind of thing. So if you have questions,
if you have questions, just post them, and as soon as I see them pop up, I'll interrupt Andrew and tell him that there's a question. If there's a particular question about a slide or something that you want to ask, you don't want to wait till the end. We're going to have a Q&A session at the end, but if there's something burning that you have to ask about that slide, just pop it in the chat and we'll get it answered. Okay. Okay. So I'll let you take it from here. Thank you, Andrew.
All right. Thanks, Mike. So I'm the CTO of Aspen Mesh. We build a service mesh platform that's built on top of Istio. Istio is an open source service mesh that's great for Kubernetes. And so this talk is all about this concept of fault domains generally for applications in the cloud, and then finally getting closer to how that interacts with service mesh, things that service mesh can do to help you get your fault domains right. And so when we talk about fault domains, it's all going to boil down to this goal of reliability. We're trying to build reliable applications, and by choosing our fault domains properly, we can achieve the right kinds of reliability. And so the first way that I like to think about this is by partitioning reliability in a kind of two portions here. So the first I think of as unit reliability. And so this is, I have some small unit, this kind of examples around software that I wrote that my team owns. And so we want to make that unit as reliable as possible. And so There, it's about software best practices. It's about thinking about design carefully. It's about making sure you have testing and coverage, things like that. Now, that's in contrast with a concept that I think of as system reliability, which is, okay, once we've made all the units as reliable as we can, we still know that we can have failures. And so how do we make the overall system that's delivering our applications reliable, make sure it works, even if components and units inside of that system fail? So what am I talking about here? What could go wrong? Well, like the first one is that team over there that's in charge of the other unit, they wrote buggy software, right? So we can't assume that the other units are bug-free. But as well, we're running on top of all of this infrastructure. And so we have to worry about failures in the infrastructure. So here are some examples. These are, you may have seen these before. These are like the classical 8 fallacies of distributed computing. So things like, you shouldn't assume the network is reliable. The network may not, just because your unit puts a message into the network, doesn't guarantee that it's going to arrive, the packet's going to arrive over at something at the other end of the network. If you're testing 2 units on your machine, the bandwidth between those units may feel like it's infinite, right? But when you're actually deploying them in reality to different data centers at different edges of the continent, you can't assume that there's infinite bandwidth between them. And so you have to understand that there are properties about the infrastructure, all the things that you depend on, that may mismatch with the assumptions that you have, or that may fail and cause problems, and yet still you have to build a reliable system on top of that. And that comes from being careful about what kind of faults you're prepared to handle, and understanding and controlling when something goes wrong, what are all the things that it can affect. So basically, even if you can fix unit reliability, you're still affected by system reliability. You still have to be prepared to deal with it and understand it. Here's an example of a system reliability thing that probably isn't front of mind for a lot of folks, but is kind of an interesting dependency that we all of us who write and have software that runs, we all rely on this. Right, so we all know at some level underneath our software are transistors. And it turns out that transistors can be affected by this thing. This is a single event effect. And so what happens is a particle, so this could be from an X-ray or from just some charged particle flying through the atmosphere and finally impacting a transistor that's in some data center somewhere, or on an airplane anywhere. And what it does is if it impacts and interacts with that transistor, kind of shown up here in the top left here, it creates all of these, it deposits a bunch of energy, and it actually separates electrons from all these holes that they're supposed to be with. And then it's gone, interaction complete, and all of those electrons will sort of collapse back to the holes that they're separated from. And that's movement of charge, which is a current, right? So down here in the bottom, you can kind of see a single event effect has a current shape that is related to this charge moving. And so that transistor may be part of a bit of memory. And so here's kind of a schematic example of that, where you've got a transistor up here, and you've got a capacitor, which is basically a bucket for electric charge. And maybe in our example, if the bucket is empty, that's a 0, and if it's full, it's a 1. Well, this particle striking it could actually cause current through this transistor up here that flows into this bucket. And if there's enough and the circumstances are right and there's nothing to sort of pull all of that back away, that can flip a 0 to a 1, right? So you can actually have some memory cell that flips from 0 to 1 through no fault of your own software, right? Just because of this random particle interaction. And that's a system thing, right? It's hard to defend against it very well in your own individual unit. And this is like a real problem, right? It's a problem at sea level. It becomes a bigger problem as you go higher up in altitude, and it finally becomes an even larger problem if you're not on the ground anymore. So aircraft that fly, across continents have to worry about this sort of thing. If you've ever heard, hey, if I fly from LA to New York, it's like getting so many X-rays at the dentist or something like that. That's the kind of same phenomenon that's driving an increased rate in single event effects. And finally, if you're not in Earth's atmosphere at all, if you're like a satellite orbiting the Earth, it becomes an even bigger deal. So much of a big deal that NASA can actually track these things and correlate failures in spacecraft to times when they know that there are more of these particles interacting because there's higher levels of solar activity or there's a solar flare, things like that. And then this one's pretty interesting. ESA has some satellites that are orbiting the Earth at a constant altitude, and they tracked the rate of single event effects that impacted their satellite, the number of times that bits flipped, and they observed that's much higher. So every little white dot that appears in this video is one of those things happening. And so you can see that there's a whole lot of these things happening in this area kind of over South America. And that's due to this phenomenon that's not all that well understood, but it's called the South Atlantic anomaly. And so this is an area where Earth's magnetic field is weakest, and so it offers the least amount of defense against these particles. And so you have a higher rate, it's more likely that you get these single event upsets here. This is pretty interesting. I was kind of practicing slides yesterday, and it happened to pop up on my Google newsfeed that there's apparently a shift underway in the South Atlantic anomaly. Its size and sort of magnitude are changing, and so we may have even more of these single event upsets on Earth as we go. And it's not a very well understood sort of phenomenon, but this is an example of kind of one of these dependencies that's underneath that you don't think a whole lot about, but it can affect your system and cause faults. So how do you deal with this example? Well, I think that this kind of maps back to the ideas around unit reliability and system reliability. So a unit reliability take might be to try to defend your individual unit, against these particles. And you can do that somewhat with shielding. And so over here on the left is an example of Juno, which is a spacecraft around Jupiter. And it has a 500-pound titanium box that all of its electronics live in to shield it from a bunch of these single event effects. But we're all probably more familiar with something more on the system reliability side. So this is an example from the space shuttle, which is the space shuttle has had a bunch of these avionics and flight control computers. And so they had 4 primaries and then 1 secondary. So they had 5 in total. And this is the main control panel for the way that all these computers voted. So the way that it worked on the space shuttle is you could have one of them was actually like commanding everything and doing everything, but all of them were fed the same telemetry. And the 4 primaries were supposed to be identical hardware, identical software loads, and so they should behave the same. The 5th one was actually built separately, totally different implementation, tried to build to the same specifications. And so you'd feed the same input into all of them, and you'd check the output, and they could all vote on each other and say which ones they thought were doing it right or doing it wrong. So like, for instance, if computer number 2 goes off the rails, then hopefully, 1, 3, 4, and 5 are all going to vote and say, that guy is wrong. And that would show up as error indicators in this little panel that, hey, 2 is off base. And probably 2 is going to vote that they're all wrong. But that's going to be just like one of these rows. And so, if you're an astronaut, to ignore that and make sure you don't let 2 be in charge because everybody else agrees that he's wrong. And so that's more like the system reliability approach that we're familiar with. And a more common terrestrial example is all of our servers have error correcting code RAM inside of them, right? Which is where you have a little bit of redundancy. You have some redundant bits that help you detect errors in other bits and correct them. Those errors could and sometimes do come from these single event effects. They also can come from other sources like just electromagnetic noise or a defect in the hardware, that maybe causes, some of those memory bits to be leaky and sort of flip back. But either way, right, that's, you don't try and solve that in every single individual program. You try and solve that kind of with this system level redundancy approach. And before we get back to kind of how all this applies to Kubernetes and fault domains, I want to say that the Juno people are not ignorant of this system reliability approach. Their environment around Jupiter is actually about 10,000 times worse for this kind of radiation than it is at Earth. And so the only way that they could get it to work was to have a big heavy shield that knocks it down by about 800 times, and then get the rest of the way there with redundancy. So inside of that box is still a whole bunch of redundant electronics and error correcting RAM and things like that. So this is kind of this unit reliability versus system reliability. The first big example of this is this thing called redundancy. And so redundancy is going to be the first system reliability approach that we kind of double click on and dive a little bit deeper. So the thing about redundancy is that it isn't cheap to do. And so it's important to build redundancy where it matters the most. And so I dug through some postmortems where there was redundancy, but where the redundancy didn't actually save or prevent the incident that caused some outage, right? So here are some examples. So Go Cardless had a Postgres database that had a standby and as well as kind of like an offline sort of write-only backup. But they were focused around the one main online Postgres system. And to provide redundancy there, they ran the disks inside an RAID configuration so that if a disk failed, they wouldn't lose their Postgres database. But then what happened is they experienced what the system reported as the simultaneous loss of 3 disks at the same time. And so all the RAID redundancy didn't save them from that. It's pretty unlikely, right, that 3 disks actually die all at the same time, maybe due to some power thing or something like that. But another common thing here can be, well, the RAID controller, just went nuts. And so it's great that you have 3 redundant disks, but if the RAID controller that's in front of them goes down, then all 3 disappear. PagerDuty, they had an architecture when they reported one of their outages. They talked about an architecture where they were running services in 2 different AWS regions. So that'd be like US West 1 and US West 2, 2 totally separate regions. But their platform relied on some external services that they got to, and finally communicating, information about pages to their users, and that went through one peering point that was shared by these 2 different AWS regions. It turns out in practice, the path to those services just happened to go through the same peering point in both cases. Well, so when that peering point had problems, even though they could successfully fail over from one region to the other, it didn't help because they still had that same choke point of the one peering point. This last one is pretty interesting, and again, kind of like outside the realm of cloud infrastructure. So in 2004, there were these power blackouts in Ohio and the Midwest, and kind of reaching all the way up into Canada. This one was pretty interesting to look at because the the trigger here was tree growth. So a tree grew into a line because it wasn't trimmed back properly. But they had redundancy. They had multiple different transmission lines. And so the tree grew into one of these 345 kilovolt transmission lines and caused a failure. And all the power that was supposed to go over this transmission line was instead, I guess, being dedicated to catching that tree on fire. So they shifted power delivery to other transmission lines. But the problem was that extra power, I guess, for power lines is enough to change a little bit of the shape, like how much the power lines sag. And so that change in sag caused those redundant transmission lines to contact trees that were also not trimmed back properly. And so they even had redundancy, but they still had these big failures because, well, now even the other transmission lines under the increased load failed, and because they finally contacted trees. And so this is one where redundancy is great, and they had redundant power lines. It's really hard to think about the idea that you might need redundant approaches to trimming trees, so that if one team or company isn't doing the right job on trimming trees, at least you might have a redundant pair that would have done a good job, and therefore your backup transmission lines would have been safe, right? That's something that's really hard to think about in advance, but it kind of goes to show that redundancy can come at a bunch of different layers, and it's careful to understand what kinds of redundancy you're providing where, and how that contributes to what kind of failures you can tolerate. Okay, so I should tell you where you should build redundancy, right? In exchange for you coming to my talk. There's a couple of different approaches to modeling redundancy. This one I think of as a top-down approach, which is pretty common in lots of engineering disciplines. And so fault tree analysis is based on, you write down at the top, you write down a bad outcome that you don't want to have happen. So in this example, it's going to be a fire or an explosion. For most engineering projects, right, fires and explosions are not desirable. If you make fireworks or rocket engines, I guess maybe that's different. But for this example, at least, fire and explosion is the bad thing. So what do you need for fires or explosions? That's the contributing events that have to happen for the outcome to be true. So for fire, well, you need air and you need fuel. You need an ignition source. And you need all of those three things. So we're going to write those down, and we're going to connect them with an AND gate. We need all of them. And then, like in this example, for ignition source, well, what could be an ignition source? So in this example, the author thought of two different kinds of ignition sources. One is somebody could just bring an open flame nearby. And the second one would be, there could be like electrostatic discharge, so static shock and a spark from that. And either of those count as an ignition source, so you link those with an OR gate. If you build out this fault tree all the way from top to bottom, then you can understand all the events that could contribute to failure, which ones are mandatory and which ones it could be either of these, right? And if you can get probabilities for these contributing events, you can even use like math around probabilities to try to figure out the probability of the bad outcome happening based on each of the contributing events inside. And then if that probability is bad, then you also know where to focus your efforts by identifying the pieces that are maybe the cheapest to fix but contribute large amounts to the overall probability of failure in the system. So this is the top-down approach. I think that the top-down approach is great for a lot of engineering disciplines, but I think that it has some shortcomings for Kubernetes and cloud architectures. So the first one, at least in my experience, is that it's pretty hard to enumerate all the failures, and it's even harder to enumerate all of the causes. there's so many of them, and it's just hard for us to think about all of them. Another one is that for our systems, failure probabilities are really expensive to obtain. So if you think about other kinds of engineering problems, you may be producing 1,000 widgets to one design, right? You've got one design, you're going to just stamp it out over and over and over again for 1,000, 10,000, a million of these widgets that come out the other side. And so you can measure, failure probabilities around those sorts of things. Our manufacturing in cloud software is a little bit different, right? We probably have fewer widgets than we do designs. If you're pushing to production, multiple times a day, you have one production environment, one widget, but you have a bunch of different designs that are changing all the time. And that rate of change makes it, especially as that rate of change increases, it becomes, in my opinion, pretty much impossible to measure things like probability, failure probabilities and stuff in a quantitative way. And it's pretty expensive to test. So, I kind of like when I look at this, the reason that I usually don't dig too deep on this approach for designing my fault domains is because I just don't think we're creative or imaginative enough to figure out all the ways that things can go wrong in advance. However, before we move on from top down, there is something really cool about the top down model, which is when you link it with postmortems and analysis of failures that have happened. And so this is related to the Swiss cheese model. So the Swiss cheese model is basically that, hey, for something to fail, right, there's usually several things that have to go wrong, and they all have to align for a failure to happen. So if you deploy something broken to production, well, the unit tests had to not detect that there was a problem because they were using an old version of the dependency or something. It had to not, nobody noticed it in staging when it deployed to staging. And then finally, when we did the Canary deployment in production, right, the Canary system wasn't actually checking for these kinds of errors that were being reported by this bad build. Maybe all three of those things have to be true. So those are your three slices of Swiss cheese, but you're not going to have, so in order for a failure to get all the way through, well, it has to go through all those layers of Swiss cheese. And so that sounds unlikely, but in practice, my experience, and I think a lot of other people's experience has been, what's really happening is that you don't have as many layers of Swiss cheese as you think, because you're already getting through several of those holes. And there may only be one or two layers that are still saving you from failures. So there could be hazards that are present in the system that are occurring that you're not noticing. And so when you look back post-mortem with something like a failure tree, you can see some of those apparent in your system. The classic one for us is like, bad backups, right? We were doing a bunch of backups of all of our data, but we never tested the backups. And so we never noticed the backup system had failed 6 months ago until we lost data in production and went to restore. And then we noticed the backups were bad. We might have alerting systems that are alerting us. We might be too fatigued to notice these. I'll post the slides. This is a link to an article about a hospital system in Boston that actually reduced alert fatigue in their intensive care unit by changing the thresholds for when alarms went off, and observed an improvement in patient outcomes. So they had fewer alarms. They were less sensitive to systems saying that a patient was ill, but because they were more careful about what alarms they did pay attention to, they had a better outcome in terms of health of their patients. And so failure tree analysis can help you see all the things that are really important that you didn't notice, and all the things that are sort of lower down in importance, and maybe reasons that you should make those less loud of an alarm in your system, or address failures in those layers differently. So that's kind of this top-down approach. Let's turn to something that is more suitable for cloud software, and that's bottom-up. And so this schema, this is kind of like a dependency, what depends on what, which you may have seen before. I'm going to use Kyle Larson. Again, it's linked down there, has a cool way of talking about this that's especially suitable for Kubernetes and service meshes. And so that's where you take applications and you write up fault domains. So every one of these things is a fault domain, and it could be an application component, or it could be infrastructure that we're relying on, or it could finally be the overall application itself. So this is conceptual drawing based on an Istio sample application. This is like the book info demo app, if you're familiar. And so in this example, we'll think about, okay, what if we deployed our application to 2 different regions? And so we have one copy running in US West 1, one copy running in US West 2, and we can fail over to either one of them, right? And so inside of there, there's the front door service that we're working on is this thing called product page. So this example is, think if you had to build a bookstore, an online bookstore like Amazon bookstore or something in Kubernetes out of microservices. So the first thing you need to do is your users have to hit a page that's going to give them all the information about a book, and that's this product page. So it depends on some subcomponents, some other fault domains. And that is the detail service that has details about the particular book, price, things like that. It also depends on this reviews service. That's where the user reviews come from for this book. Larson's model allows you to differentiate between these two in an interesting way, which is that the detail service you rely on, but it has redundancy. The review service, it has redundancy too, but it's also what's called ignorable. And so that means that product page can consult it, it enhances the system, but if it's not available, product page should continue with just what it got from its other dependencies. That makes sense for things like book reviews, right? Having book reviews show up on the web page probably makes it more likely that somebody would purchase something, so they're great to have. But if they're down, we would rather return the details, the price, and all that sort of stuff, and give users an opportunity to purchase it instead of just throwing an error all the way back to the users. So that's what an ignorable dependency is. And then finally, you may have dependencies that are neither redundant nor ignorable. And that's, in Larson's terminology, these cascade things where if they fail, there's no redundant fault domain at the same level. And so the thing up above better be prepared to handle that failure or will fail itself. And so this is just kind of the terminology associated with Larson's fault domains. So a fault domain is something with a shared single point of failure. A level is a set of domains serving the same purpose. Okay, so we've talked a lot about fault domains, but we promised to talk about Kubernetes and meshes, right? So time to bring in meshes and start talking about, cool, what can a mesh do for me with my cloud application? So I'll do a quick introduction to service meshes. So this is an architecture that doesn't have a service mesh, but it's built around microservices. So there's 3 different microservices, A, B, and C, and they each have their own logic, their own code inside of them that makes them do whatever they do. So these could be, from that book info example, they could be the product page and the reviews and the detail service. It could be whatever. So service mesh people look at this drawing and observe kind of 2 broad things. The first thing that we observe is that the communication between services is like is solved and managed in a pairwise fashion, right? So A talks to B, and in this example, A is built on Python and B is built on Java. And so A is using Python's HTTP library, B is using Java's HTTP library, or maybe Spring's HTTP library, And then, C might be using Node.js's library. And they're all going to be slightly different and have slightly different behaviors. And so things like how A discovers B might be slightly different than the way that B discovers C. The way that you give a certificate to use to authenticate that service B is really who it says it is might be different than for another pair in this pairwise communication scheme. And that doesn't mean that it can't be done. It just means, there's a lot of, there could potentially be a lot of these different pairs running around in the system that we have to think about. So that's one. The other big category here is that observability and monitoring is implemented in each application. And so and there may be some common underlying like system, like an APM or something that's collecting all this information from each one of these running microservices, but it's still inside the service itself to collect information about how healthy it is, whether it's having success or failure with requests, any of that information that you might need to observe and understand the internals of that service. So there's a little bit of a burden on the application teams to produce all that observability information. There's also an opportunity for inconsistencies to creep in that make it hard for things that have a global scope. So an example here would be in service C, maybe request failures are spelled, request failures, and it's a counter, and it's camel case. And in service B, maybe it's snake case, and it's a rate of how many per minute. That's not totally impossible, but it's just a little bit of friction if you're a platform operator or a dashboard builder or something like that who's trying to deal with service B and service C. So what service mesh people do is they look at this and think about, well, okay, we could add something to add some commonality here. And that's this service mesh sidecar in Istio that's built around this process Envoy that runs in the sidecar container. And so Envoy takes care of all of the communication between services. And so that means that all that stuff around service discovery, policy, security, and TLS, things like that, if you can cram it into one Envoy in one way, that also applies to the other envoys in service B and service C. So there's a consistent implementation and consistent behavior. As well, all the information that Envoy can collect, telemetry, request error rates and successes, latency, things like that, distributed traces, like records of all or some of the transactions that went in and out. Those are all going to be collected by Envoy, a common implementation in every sidecar, and so they'll be done common in the same way. So you get this benefit of consistency across all of these things. To do this, you need something to both deliver that configuration and capture the telemetry back out. And so, for Istio, there's a distributed control plane that runs that's integrated with your platform, like Kubernetes, to be able to sort of store all the configuration, discover all the services, feed everything down to that data path, so that it can implement that commonality. So that's service mesh in a nutshell. Now, what does that have to do with kind of fault domains? So we were talking about redundancy as kind of our first use case here. And so there's some easy things that a service mesh can deliver for you around redundancy. So first is that service mesh has load balancing approaches inside of it, so it can make sure that work is distributed across all of the redundant the redundant instances of a service, of a dependency. It can do health checking, so it can detect that, hey, there's high levels of errors for requests to this instance of this service. So I'm going to not use it for a while because I think it's unhealthy, and I'm going to prefer these other instances. Another one, so we talked about ignorable dependencies. Istio and Envoy have timeouts and circuit breakers. And these are ways to cause, so timeouts, for example, help you make ignorable services be ignored faster. So it reduces the cost. So the example here would be product page depends on these two components, reviews and details. But we've decided that we can actually ignore reviews. So it sure would be a shame if instead of failing, reviews just got really, really, really slow. And so what happened is we would go get our details information really quick, and then we would wait around for reviews to finally fail after a few seconds, and then deliver our response without reviews. You can solve this in the application, but you can also use Service Mesh to say, well, by configuration, I've decided we should never wait longer than this long when product page is talking to reviews. So that way we can prioritize getting an answer out even without some ignorable dependency information if we need to. So that's kind of the first level of redundancy. Let's take a look at fault domains from the perspective of kind of your cloud provider, whether this is a big public cloud or an internal platform team. So your cloud provider thinks about usually at the top level, there's this concept of regions that are totally independent of each other. So in AWS terminology, like this would be US West 1 and US West 2. So they're different geographic locations. Then inside of so that's like one, those are two fault domains inside of the same fault level in Larson terminology, the region fault level. Then even inside of a region, inside of US West 1, there's a different set of fault domains called zones in some clouds, availability zones in others like AWS. And so these are also redundant. And so you would have an availability zone, US West 1A, 1B, 1C, in the US West 1 availability zone. And then, somewhere under there is your stuff. And it could be running in one AZ, it could be running in multiple AZs, it could be running in multiple AZs in multiple different regions. That's kind of up to you for how you organize it. And then finally, you may depend on some services that are global, right? So examples of these in AWS would be like Route 53, and IAM have global components. And so, AWS tries really hard to make sure that they're very available, and as much as they can, there's sort of like redundancy and logic pushed closer to the regions to minimize the likelihood that you have an outage there. But yes, if you have a Route 53 outage in AWS, it's a big deal. It could affect all of your applications, even across different regions, right? So let's think about service meshes for this fault level of availability zones within a region. Here we're going to add in a second aspect of system reliability, which is locality preference. So if you're familiar with Kubernetes, Kubernetes can run across multiple zones. You can have one Kubernetes cluster that is spread across 3 different zones in this example. And so when you do that, you have one master in each zone, and your workloads are distributed across each zone as well. And so if a zone goes down, then one of these masters dies or loses connectivity to the other masters, but the other 2 masters can still form a quorum and proceed. And they can create new workloads. They can replace the workloads that died in the zone that went away. And they can proceed while you're recovering the other availability zone, either because AWS has to restore that availability zone, or because you misconfigured something and now you have to make that master in that availability zone healthy again, right? Either are, of course, problems that either are possible, but your fault domain of availability zone is your unit of failure that has this single point of failure. And if you're running multi-zone Kubernetes, your Kubernetes cluster can survive the failure of a fault domain that is an entire zone. You can just do this with Kubernetes, but what's cool about a service mesh is that Istio supports Istio and Envoy support locality load balancing. And so this is a model where you prefer the local instances when possible to save money, but you can fall back to instances in the other zone when needed. And this is because in most of the big public clouds, the traffic inside of one availability zone is free, but traffic across availability zones costs a little bit. And so here's a report from an Istio user. This is Carl Stoney from AutoTrader. They run a lot of Istio. And when they turn on locality load balancing, they save $3,000 a month because most of the time they can keep all the traffic inside of one availability zone. They're only using the inter-AZ traffic when they have failures or workloads that are only deployed in one zone for whatever reason. So that's a cool example of how locality preference can help you still choose redundancy by making the costs sort of reasonable. And cost is dollars, but it's also things like latency and just reliability, all these things where if you can stay within one zone, it's a little bit easier. So okay, so that was the AZ fault level. Let's think about the regional fault level next. Can we just do the same thing again? Not really. Not at least not with Kubernetes directly. So Kubernetes has multi-zone support, like we talked about, but this is from the docs for Kubernetes. You cannot run one Kubernetes cluster across multiple regions or multiple cloud providers, at least not if you want to use all the stuff that's built in and supported in Kubernetes. The first reason for this is latency. So usually regions are actually geographically separated. And so it's the big wide internet between them, or even if it's a private network, it's still a geographic distance. Latency is higher. So operations with a control plane that's separated that way would be slower. There's also some things in clouds like volumes and things like that that have affinity to one region, and you need to do something special to move it somewhere else, right? And you could do all that special stuff, but Kubernetes has decided that you really actually don't want to because of this thing around availability, which is if you do all this work to make one Kubernetes cluster that can span even different regions, well, now your fault domain for a Kubernetes cluster failure includes your region, right? It includes all your regional redundancy. And so to do this right, the correct control plane fault domain for Kubernetes is not all the way up to the cross-region level. It's at the cross zone level. So it should be inside of one region. And so for that reason, Kubernetes, anti-recommends doing a single cluster that spans multiple regions. But let's, if we go back and we look at our multi-cluster example where we had these different clusters, we do have the same service running in both of them, this detail service. So is there something that we can do? Like if we have to get rid of details from one, can we just use the details from the other? Well, Service Mesh Istio can help with this. So Istio does allow running multiple copies of Istio. There's a couple of different ways that you can do it. We recommend the model that matches the Kubernetes approach, which is replicated control planes. So just like you'd have two Kubernetes clusters, you'd have two Istio control planes in this model. And so then if you want to reach from this cluster over here on the left to a service in the cluster over there on the right, you're crossing from one Istio control plane to another Istio control plane, but you're still having the same sort of service mesh sidecars talking to each other. There's some details around this and some of the trade-offs that are inside of there. We focused on independent fault domains here. There are some other considerations like trust domains and networking and things like that. Down there on the bottom is a link to an article on InfoQ that goes deeper on this as well. There's updated Istio documentation that talks about some of the trade-offs inside of here. We generally recommend doing this multiple Istio control plane approach. But inside of there's something interesting that also affects system reliability because of the fault domains here. And this is related to whether your system, what parts of your system, how much autonomy they have from other parts of your system. And so the example here to think about is in that multi-cluster case, this is a simplified drawing of what's happening from a security perspective in that case. And so you have a service in one cluster that wants to talk to a service in the other cluster. And in service mesh, these are protected by mutual TLS. So there's like X509 certificates and TLS handshakes involved. And so the connection between these two services, is on the order of seconds, how quickly they're made and how long they might last. And so if the provisioning but they have to sort of be linked by this common trust domain. So A has to have some reason to trust when it talks to the correct B, trust that it is B. And that comes from these certificates. So if certificate distribution happened at the same order as the connection establishment, then there's not any autonomy. And a failure at higher fault domains related to certificate distribution can instantly affect services. But in Istio, there's actually two different levels here. So the first one is the identity provided from this intermediate certificate authority down to the workload that, maybe in a healthy production deployment, this might last for hours or days or something like that. And then finally, there's over top of this root certificate authority commonly that's going to create the certificates for each cluster to use to sort of sign certificates for each individual workload. And so this positioning and updating and rotating of these certs can happen at an even slower rate. So this, could be happening in the rate of weeks or months or even years that you're replacing the intermediate certificate authority. And so if you're doing that, then a failure, a fault up here, right, that affects this fault domain of the root CA, doesn't instantly break everything down below. It gives you time to detect that failure and recover while these things still proceed because they have autonomy. They're not in time as closely coupled to this root CA. And last one here, auto-scaling also touches on system reliability. This deserves a little bit of justification. Auto-scaling doesn't at first blush sound like it's the same thing as reliability, but I argue that it is related. Autoscale is an aspect of reliability. As we've talked about, you can't just stamp out redundancy without consideration for cost. You will always be challenged to decide where you're going to build what kinds of redundancy to handle what kinds of faults. How efficient can you spend your dollars, your time, your CPU cycles, your cloud credits, whatever, to get the most reliability out of it. And then finally, saturation, which is what drives auto-scaling, is really just a mile marker on the road to sort of failure, right? So first you're not saturated, then you're saturated, then next you fail. So saturation is definitely about reliability as well, right? So auto-scaling is a technique to enhance reliability and performance. Kubernetes provides horizontal pod auto-scaling, which is based on this idea that you just stamp out more pods if you observe metrics that indicate that you're reaching saturation. So without a service mesh, some are readily available to you, like CPU usage of a pod or memory consumption of a pod. But if you have a mesh, you automatically get the opportunity to do a couple more that are, in my opinion, closer to the user expectation around performance. So you can do things like autoscale based on request latency. You can autoscale based on error rates. And my favorite, you can autoscale based on queue depth. So if queues are growing in size, then you can tell which you can tell from the sidecar, like the sidecar has a bunch of requests, but the application hasn't finished processing them yet. Well, now it may be time to scale up that application because the queues are growing and we know we're going to reach a point where we can't keep up. So kind of wrapping up here, we talked about the difference between unit reliability and system reliability. Unit reliability is, of course, great. It's a very important part of software development, but it doesn't save you from having to think about system reliability concerns. You still have to deal with those. We talked about ways to model fault domains, and I talked about this approach, this kind of bottoms-up dependency approach, using Larson's concepts around redundant and ignorable and cascading to kind of organize and manage your fault domains. We talked about redundancy as kind of the most obvious way to create reliability across fault domains. But we also talked about how you need to consider things like the cost of that redundancy and how you can use strategies like locality preference to help manage that cost. And then autonomy, which provides kind of a measure of redundancy across time for different fault domains that prevents a failure in one fault domain from instantly affecting another fault domain that depends on it. And that gives you an opportunity to recover. And then finally, we talked about autoscaling as a way to accurately size things inside of a fault domain to make sure that you're getting the most out of the redundancy that you're paying for in terms of making reliable services for your users. So with that, I'll stop and I'll just note that Aspen Mesh is hiring right now. So if these are the kinds of things that are interesting to you, we'd love to talk to you about the kinds of things that you're working on. And also if you need help dealing with fault domains and service meshes in your architecture, Aspen Mesh is here to help with that as well.
Well, thank you, Andrew. That was a very interesting talk there. I was going to mention, hold on a second here, I changed this incorrectly. Here we go. So I kind of had a question myself about, you were talking about not having multi-site, I guess multi-zone clusters, but because a lot of it is heterogeneous, but are you able to build like a mesh cluster in one cloud provider and have another one in another one for redundancy?
Yeah, that's a great question. Yes, you can. So maybe let me scroll back kind of to this slide that shows some of the architectural pieces here. So this cluster one is a Kubernetes cluster. As you say, one example is these are running in two different zones in the same cloud provider, but they could be running across cloud providers. They could be running one in a public cloud provider and one in a private cloud that's built and owned by your organization, or multiple different private clouds built by your organization. We see that happen a lot, especially one might be cost. The other one might be application maturity. Like maybe there's parts of an application that just aren't yet compatible with running in
like legacy applications,
A or B, right? The third one is compliance. Maybe parts of your application that just hey, our security posture is that this stuff is staying on-prem for now, or maybe forever. And so you can definitely have a cluster that is only on-prem and deals with that most sensitive data. And you could have a cluster somewhere else, and you could use service mesh to securely connect services in one cluster to services in another cluster. So absolutely, it's not exclusively about redundancy.
That's awesome. That's great. Let's see. The only thing I have here, a comment from one of our viewers, said, "Nice talk. Thanks. You liked it."
Oh, great.
Yeah. If anybody has any additional questions you want to post, we have a few minutes here. So, just feel free to post any questions. I also put a scrolling there to follow Andrew on Twitter as well, and Aspen Mesh. Both of them are on Twitter. You can follow him there. He has his. I think you have your DMs open, right? Your direct messages open.
Yep. I'm
So you can
answer questions via chat, or now later. Find me on Twitter. Happy to answer questions. And the Aspen Mesh and others in the Istio community try to be super helpful. So generally, we'd love to talk about people and things like like the use cases that we talked about around locality preference and things like that. A lot of them come from Istio users who say, hey, I want these sorts of things, and so we love to hear use cases in the Istio community broadly, and for sure also in Aspen Mesh specifically. We love working with our users on particular corner cases and things like that need architectural help or just plain features.
More comments there. Great info.
Oh, thank you. Thanks, SK.
Yeah, it was super.
Hey, Zach, thanks.
Yeah, pure soul.
Oh, thank you.
Yeah, it's a great talk. I mean, I guess the other question: how are you guys dealing? I know there's a lot of virtual meetups happening, virtual conferences. How are you guys dealing with the pandemic and everything going on around the world? Is it business as usual? I mean, because most of you, I think the majority is everybody's remote, right? Anyway, for the most part.
Yeah. So Aspen Mesh has kind of an interesting story here. We are primarily based in Boulder, Colorado.
Right.
So probably 90% of the team is located in Boulder, Colorado.
Uh-huh.
And then, when COVID hit, we all, started working from home, working remotely, even though we're kind of mostly in the same geographic proximity. But, also that means that, now that like everybody else, pretty much we're fully virtual and fully remote, that it makes it easy for us to work with other people who are also remote, either users and customers, and also
and all this product is all in the cloud anyway. So I mean,
right.
So it makes it even a lot simpler.
Yeah, it was more persons than technology. I'm a person who has never worked full-time remote before, and so it's definitely been a transition for me. But just try to learn from the experts who have done it before, and make sure I communicate a lot and do all the things to keep connected. And then like on a outreach and like going to talks and events and things like that. Yeah, I mean they're all virtual nowadays. That's great because they're consumable, in the moment, but also usually offline, like videos and things like that. So it's all about just making sure that you've got the right format for the consumption that your audience wants to participate in.
Right. Here's another comment coming across here.
Oh, cool. Thank you. Thanks, Michael.
Yeah. So let me ask you this. I mean, for the most part, all of this stuff that you were talking about is all open source. So do you have any projects on GitHub or?
Yes. So most of what I talked about is built into the open source service mesh that we're built on itself, Istio. And so you can do all of that. Aspen Mesh as well has some open source projects, and some of those have actually moved back into Istio proper. So like, I guess one of our first examples was we had a configuration error detector that we open sourced as a side project, and a lot of people in the community were working on it, and eventually we migrated that sort of back. And so our project was called Istio Vet, and there's now Istio Validate just built into Istio automatically. Then as well, Aspen Mesh has some proprietary integrations and enhancements on top of that. Some of that's related to mainly our thrust is around helping some of the largest enterprises on the planet be able to adopt and use service mesh. So they may have specific certificate authority, integration requirements, things like that we do. They just need architectural help figuring out the best way to build this. They need us to help make sure that bugs are fixed and releases are stable and all of that sort of stuff. And the other thing that's a big problem for enterprises is being able to understand application health. So our experience and our data from our users has been that, like, oftentimes they're spending more time, like significantly more time, figuring out where a problem is than they are solving, like actually getting somebody to solve the right problem, right? In an on-call, like everything's down, things are on fire. They may spend 6 hours finding out where the problem is, and then 15 minutes trying to get the right person on the phone to look at it, and 40 minutes fixing it, right?
Right.
So we have tooling to help you, eliminate that 6 hours by helping you localize the problem very quickly using Service Mesh, and then also be able to understand a lot about the root cause of the problem. So what else was happening when this happened, and what things is this related to? What connections are happening? What is surprisingly different about the communication now than it was an hour ago? We can show you like what distributed traces are most novel relative to all the traces that you had before, and help you understand what's actually going on in your system. That's all built on top of this open source foundation.
Gotcha. And I mean, you guys must have clients all around the world. So, so in anywhere, Europe, South America, Australia, Asia, all over. So how do you deal with the security piece, or how do you have it built into it?
Right. So for the security itself, one thing is we try really hard to help make sure that Istio and Envoy are secure.
Gotcha.
So we participate in security there. There's a security working group that we have leadership on, and we participate in finding CVEs and trying to fix vulnerabilities in the underlying product itself. And then we try to use secure methodologies for anything that we build on top of it. Use the best security practices.
Right.
As a note, Envoy, that data path component at the core,
Gotcha.
is one of the mature CNCF projects, and has undergone like a third-party security audit that it did, in my opinion, very, very well at, and was complimented on for kind of like fundamentally secure choices in architecture.
How do you spell that? Envoy?
Envoy. ENVOY.
VOY. Envoy. Okay.
And so that's where we start. Other things is Aspen Mesh is an incubation project from a larger company called F5 Networks.
Right.
That's well known as a provider of like sort of secure infrastructure.
Yeah, F5. Yeah, definitely. F5 is a big company.
Yeah. So we do whatever we can to absorb any security benefits from them around best practices or expertise or things like that.
That's a good thing to build on. Let's say anybody else out there have any burning desired question want to ask Andrew? Maybe ask him why his Twitter is not that Jenkins. We already mentioned that earlier, but
it really is. I joined F5, and I started getting emails for somebody was blaming me like, hey, Jenkins sending me all this spam. Like, can you stop it? And I was like, I'm not that Jenkins. I am a Jenkins. I'm not that Jenkins.
That's hilarious.
I'm the administrator. That is a true story.
That's hilarious. Yeah, if we don't have any more questions, I think we're going to just call it a night. And I really want to thank you, Andrew, for coming on, and Aspen Mesh for being part of our meetup. And we'll see. Maybe we'll have something else for you to present soon.
Yeah, absolutely. It was great being here, Mike. Thanks for having me.
Not a problem. Well, thank you very much, and you have a great evening. And for anybody that joined in late, if you have any conferences you want to attend or meetups, follow me on Twitter, MikeRossTX, or usually the DevOpsDays.org. We have plenty of virtual conferences happening all around the world, and a lot of great speakers as well. So just go up there and pick a conference you want to join and just join. Some of them are free, some of them are paid, but take your pick and see which speakers you want to hear. So, well, thank you very much, Andrew. We'll talk to you later.
All right. Bye.
Take care.
Everybody.